thing just came out. All right, thanks. So welcome, everybody, and thanks for taking the time to attend the session on MySQL on I/O memory. Really, the session is more generic, as I'll be talking about various solid-state technology options in the market today. So I've designed it in a way that it is generic, and my goal here is to present you with all the options, give you the knowledge that I can, and enable you to make your own decisions. Before I get started, as Erin mentioned, you have a card that you need to fill out, and the pen, you take it with you. I don't know if you noticed, but if you click it 3 or 4 times, it lights up. You know, we like to show people the light, so it kind of goes well with that. There you go. And at the end, you know, if you feel like it's in a concert mood, you can do the candle thing. And of course, when you fill out those cards, we'll be using those cards to draw one of them, and one of you will walk away with an iPad. Now, why iPad? Well, it is a pretty cool device, and there is a second reason for it. So it turns out that Apple was founded by 2 people, as you know, or at least 2 main people, Steve Jobs and Steve Wozniak. And Steve Wozniak, who I'm sure doesn't really need to work for anybody, actually works for Fusionio. So he's our chief scientist, and he saw some value in this technology that he wants to become part of it. Yes, sir. Sometimes. We have to keep him away from the lab, otherwise he spends too much time in there. But yeah, it's fun. You know, if you ever come to our offices, sometimes you actually see him rolling around on his Segway. It's pretty cool. Yes. So let's get started. Oh, one last thing, please. If I may, I know, you know, as we go on, people will have questions. But what I would really prefer is if you actually held on your questions till the end, because that allows me to basically go through my presentation and maintain a continuity. As sometimes the questions, you know, they require you to go off tangents. And also, I have a couple of colleagues of mine come over here, Mitch Crane and Jamila, and they work with me, and we are sort of brothers in arms. And I'm glad that they came here to support me. In the end, when we start the QA session, if my skill level is not enough, then they will jump in and support me with your questions. So thank you. If at any point, Erin was very particular. She told me that, look, you know, this can't be a marketing presentation. So at any point in time, if you feel like I'm getting into the marketing turf, please break my rule and tell me to stop. Right? But my goal really is not to sell it. My goal is to educate, and I will tell you why. So before joining Fusionio, I was the VP of IT/DBA at Wine.com. Now, Wine.com is not a MySQL shop. It is a Microsoft SQL Server shop. And by heart, I'm a DBA. You know, I work with databases. I like that world. I like what DBAs deal with. And I got a chance to implement the solution at Wine.com because they were having some serious problems that were not easy to solve or were very expensive to solve. And when I implemented this, I saw something that was just amazing. And I said, I have to work with this technology. What I do now is my goal really is to go around and educate people, to get them excited. You know, I don't care if you buy it or don't buy it, but what I do care about is for you to get excited about it. It is such a cool technology. It allows you to solve some pretty amazing problems. We have a lot to go through, so hopefully I will maintain your interest. The best way to get into SSDs is to really ask yourself, why SSDs? Why solid-state technology? And then, as we know, it has been there for a while, but has the time come now for this technology to be used in production? Is it ready for prime time? The best way to answer that question is to actually look at a couple of real implementations where people were confident enough to use this technology in their production environments. Number one. Number two, when we look at these implementations, we learn how they used it and what were the problems that drove them towards this solution. So to start with, I'm going to look at Cloudmark. So Cloudmark pretty much deals with spam, phishing, viruses, and protecting against those things. They are pretty massive. They have 1 billion subscribers in over 190 countries. But ultimately, it boils down to this. What did they have before? So they are obviously a MySQL shop. I picked them because of this crowd. And they have set up their MySQL boxes in a master-slave replication model to deliver their high availability. Also, they have multiple slaves to each master for two main reasons. One is simply disaster recoverability and high availability, and second, to distribute the reads and writes, again, to deliver more performance. But they were having issues. Regardless of what they had, they were having performance issues. And they found that it was clearly a case of disk I/O bottleneck. And then they were having the problems with their storage arrays. Because what they found is that you have these things which have really large and huge footprints. The vendors say they are reliable, and yet they're not. They always fail in one way or the other, and they're expensive, and they're hard to maintain. They wanted something better. So they looked at the solid-state technology options, and I'm glad to say they picked Fusionio. This is what they chose. This, I hate to say it, but in simplest terms, this is a hard drive. It's a disk drive. But it's a pretty unique disk drive, and if I may borrow Steve Jobs' words, it's a pretty magical device. I'm going to pass it around so that you can play with it. Don't worry about burning it. It's already dead. But the point is, that is where the storage is. And as opposed to relying on external boxes that contain hundreds of drives or thousands of drives, or relying on SAN, you take this and you plug it inside your server. And that is exactly what Cloudmark did. Now, what did they get? I don't want to read the slides, but in the end, they were able to replace enough storage arrays that they got rid of 180 spinning drives by simply 8 of those. 8 of those and 180 spinning disks. Oh, exactly. So in the storage world, what is one of the main purposes of aggregating a lot of disks together? Exactly. Because if you look at a singular spinning disk, it really hasn't evolved that much. The most you can get in terms of IOPS from a single spinning disk is 250 IOPS, and that's it. If you need any more than that, you simply have to aggregate more disks. Same with throughput. But we have multiple capacities. The card that is going around, that's at 320 gigabytes. We also have a card that is 640 gigabytes in size. And this is simply to show that when they used this and when they needed more space, they were now very happy, because as opposed to again going out there and buying racks and racks of arrays, they just buy a few of those drives and it's done. Now you would think that, oh, so we are replacing so many disks with so fewer disks. Are we going to sacrifice performance? But obviously not. The whole goal of this technology, the promise of this technology, is to drive performance. As time goes on, people are finding more use cases for it. People are finding that the benefit of this technology goes beyond performance. But it starts with performance. It starts with that pain point. Well, they saw a 5 times performance improvement. It's very important to note such kind of improvement metrics. We have tons of case studies where people see 10 times performance improvement on what they're doing, 20 times performance improvement in what they're doing. What's important is that when you look at something like this, and when you try to figure out pricing, you are bound to get into this mode where you will calculate dollars per gigabyte. And you will say, my God, this is expensive. How can anybody afford it? Well, the thing is, you need to calculate the cost effectiveness in a context of what you need to do. If you need to drive 5 times performance improvement or 10 times performance improvement, what is the cost of that? What will you have to pay if you didn't have a technology like this? Let's go to answers.com. Pretty popular website. The funny thing is, although it is 18th in the US, the whole thing is actually set up in Israel. The whole operation is in Israel. I found that quite amazing. So I'm sure Percona would love it, but they actually use Percona plugin for MySQL. Same challenges. They need to keep the website busy. They need to keep the website, is busy, and they need to keep it fast. And again here, they were using a massive number of slaves off of their master just so that they could support the website, just so that they could satisfy the reads fast enough. This is what it looked like. That's a cluster of read servers, read slaves. And yet it wasn't enough. They were not getting what they wanted. I like the way they said it, but it literally is this simple to install this card in a server. Compare this to configuring a storage array, configuring a LUN, configuring a SAN. How long does it take to properly tune those things and configure those things? This thing, you just open your server, you install it in, you load up some drivers, and you're done. These are the kind of performance numbers they saw. They went from being able to serve 350 queries per second through 3,500 queries per second, a 900% improvement. Again, what is it worth? What should it cost to drive that kind of performance improvement? The application response time increased by 30%. Replication, which was an important factor for them, improved by 3,000%. Went from more than 6 hours to 12.5 minutes. And full database server recovery went from 8 hours to 55 minutes. Talk about business value. So that's a before and after. Look at the size of that infrastructure. So they started from the point of view of performance improvement, because that is what was killing them. But what did they end up with? Look at the size of server reduction to their infrastructure. It's amazing. In the end, I mean, they're laughing on the other side of the face. It's made their infrastructure so simple to manage. As you noticed, I didn't really want to spend too much time on the case studies because I just wanted to give you an idea of how to use it and what people do with it. So let's start by just addressing the core problem. Obviously, we are here to talk about I/O bottleneck. But why? Why has it become so prevalent? So it primarily is a result of unbalanced systems. What has happened over time is that the rate of evolution of CPUs has been very significant. So on evolutionary chain, CPUs are way up here. Compared to that, the disk subsystems, the spinning disks, have really evolved to the degree of mediocrity. They're right over here. CPUs are over here. As a result, what happens is most of the times the CPUs are underutilized. Why? Because they are always waiting for the disk subsystems to service them. And the disk subsystems aren't fast enough to keep up. What a waste. And yet, the likes of Intel, they keep on giving us more powerful CPUs, faster CPUs, more cores. And again, there is a good reason for that. The evolution of spinning disk is limited by the laws of physics, by laws of motion. The spinning platter can only spin so fast before it starts losing data and reliability. But on the processor side, not me, right? Whereas on the processor side, there are no moving parts, there are no moving components, and therefore that piece of technology is prone to significant improvement. So what this has done is you may set up an infrastructure and you may start with a disk subsystem profile that works for you today. But when your business doubles, when your demands double or triple, that profile is no longer good enough. I will again take an example. I'll make an example of Wine.com. So Wine.com has a very seasonal business. Their business volume in the month of December is 10 times the business volume of any other month of the year. And the reason for that is because people love to give wine products as gifts. They do a lot of business during the month of December. So how do you design your storage system to handle for that? Do you just design a performance spec that works sort of 11 months out of the year, and then you go and do a temporary upgrade for the month of December? What happens if Wine.com then goes and buys another business? These were some of the real problems that Wine.com was facing. And that was the reason why I, as a DBA, had to go out there and look for a solution that was more long-term, which was more set it and forget it. You've used it, you've implemented it, now you can focus on other better things. So to understand the performance characteristics of a disk system, really there are three main terms that we should understand. The input-output operations per second, or IOPS. So this is simply how fast the reads or writes are happening. Throughput, or bandwidth. This is usually measured in megabytes per second, but again, cool technologies, cool solid-state storage technologies are changing that. And it is getting into a territory where now this throughput is being measured in gigabytes per second. And this is simply at what rate the data can flow from one place to the other. And then disk access latency. This is the delay that is caused when the CPU or the processor asks or makes a request to the disk subsystem. How long does it take for that request to be fulfilled? Depending on what your database model is and what your database is doing, if it is OLTP, then you really worry about more random read and writes. And I suspect that is primarily the case with MySQL databases. And here, the IOPS and latency play a more important role. Now, if you have OLAP environments, where you are doing a lot of analytics, data warehousing, then you are churning large record sets. So there, you mostly do sequential reads and writes. And here, not IOPS, but throughput. How many megabytes per second can you churn? That's more important. And latency always plays an important role. Before we understand the solid-state technology options, we need to understand the limitations of native NAND flash. As you saw that card, it has these black squares, which are essentially the NAND flash. This NAND flash is the same NAND flash that I have on my iPhone, you have on your MP3 players, whatever. It is the same NAND flash, no different. And this native NAND flash has some issues. For example, it has limited write cycles. You can only write to it so many times. So if you look at this chip, you can visualize that it has pixels, and you can write to each pixel. You can write to each pixel a limited number of times. And there are primarily two kinds of flash, SLC flash, which is single-layer cell flash, and MLC flash, which is multi-layer cell flash. The thing is, MLC is denser. And the way these things store data is by distinguishing between voltage levels applied to those individual pixels. SLC only needs to store two distinct levels of voltage levels. So it needs to differentiate between only two levels, whereas MLC needs to distinguish between 4 different levels of voltage. So as you can imagine, because of that, MLC will lose its ability to distinguish the difference between 4 levels much sooner. That is the reason why MLC is said to have less write life than SLC. Well, a lot of people don't understand that very well, and they take these limitations of native NAND flash and they apply them to all the SSD solutions out there. They apply them to all the solid-state technology options out there. I still run into people who say, "Oh, I can never use it because it has a very limited write cycle. It has a very limited life." The point is, yes, native NAND flash, correct. But when the likes of Intel, Fusionio, Ramsand, and so there's so many other companies that are coming up with these products, they wouldn't be coming up with these products and trying to deploy them in the enterprise world today if they were not reliable. Also, writes are actually quite slow to native NAND flash, not to the finished product as a whole. And that's because every time they want to do a write to a pixel, they actually go ahead and have to erase the data, called the write erase cycle. So there are some common technologies that companies use to overcome some of these limitations. So for example, how do you overcome the natural limitation of life? So what you do is you essentially establish yourself a bank of these chips, and then you write an algorithm that makes sure that you don't wear out any pixel unevenly. In other words, even if you're rewriting the same data, your algorithm makes sure that any kind of write activity is spread across all the pixels uniformly. And when you do that, you actually get a much bigger life cycle out of the finished product. How do you take care of the fact that it's natively slow to write? So what you do is you figure out a way to collect all those writes, and you batch them. And then you have a batch process, which is called the groomer, that runs at fixed intervals that can go and apply your writes in a batch, as opposed to each one doing individually, because then that will make this technology very slow for writes. So that essentially leads to another myth about this technology. A lot of people you will meet will say, yeah, I like solid-state technology, but it's not really meant for write purposes. So unless you have a completely read-only environment, it's not for me. Not true. By the way, after you leave, I have some documents, some brochures for you at the table at the end, and there's some really good stuff there. There is case studies, there are some spec sheets. So because I don't want to be reading spec sheets for you. I don't want to be telling you, oh, look at that, my product can do 200,000 IOPS, or it can do what? You can get the information from the spec sheets. But if you do want to take it with you, please know that it's there. So now I would like to go into how different companies, different vendors are trying to provide the benefit of solid-state technology to you. So one class is SAS SATA-based SSDs. So these are the ones that you more frequently hear. These are the Intel drives, the Samsungs, OCZs. These are the kind of drives that people want to plug in their laptops, in their PCs. And one thing you will always notice is if you're looking at Gizmodo.com or Engadget.com or any of the gadget sites, these things, they're still coming out. New vendors come out with them every day. But look at their performance specs. You will always see that it can read in the range of 250 to 300 megabytes per second, similarly for writes. But that barrier, there is a barrier, and they can never quite cross that barrier. Why? There is a good reason for that. So the good thing is it's very common, and you just plug them in your server or plug them in your PCs, and sometimes you don't even have to load any drivers. They pretty much plug and play. They're very inexpensive. But the point is, they somehow fail to deliver on the promise of performance. And the main reason for that is their interface, because they are bound by the SAS SATA interface. That creates two problems. One, there is a cap on the interface system itself. So I believe the latest protocol that is just beginning to come out is 6 gigabits per second. That's the latest, highest performance you can get from these SSDs. 6 gigabits per second roughly translates to 700 megabytes per second. What this means is that you can take any number of these drives and you can try to rate them, but you will never drive performance beyond that 700 megabytes per second. More than that, if you do want to use these drives and you want to deliver any reasonable capacity, you will have to use multiple drives, and you will have to use a physical RAID controller. The problem with RAID controller itself is that, number one, it becomes your single point of failure, and number two, it itself becomes a bottleneck on the performance potential of your product. DRAM-based SSDs. So there are companies like Texas Memory Systems, and what they've done is they have created these big boxes, and they have simply put DRAM, they've populated them with banks of DRAM, and they have built systems, batteries to make sure the data gets persisted, and they've created a device out of it. So they do deliver good performance, and they do deliver very good latency. The point is, they're very, very expensive, they're very large, and because they're using DRAM, now, as you know, DRAM by nature is not persistent. It doesn't store the data. So they have to come up with a lot of technology. They have to put together a lot of technology to make sure that, number one, data gets loaded properly when they initialize, and number two, when it turns off or when there is sudden power loss, how does that data get persisted? Imagine if you have a device and there is a terabyte of DRAM-based storage in there. That means if you have a database that is 800 gigabytes residing on it, when somebody pulls a plug accidentally, that device has to have enough emergency power to make sure that the data gets persisted to some sort of persistent storage. So it's taking a chance. It's complicated. Pure DRAM solution, I mean, if you look at DRAM, there are no moving parts, and it is, so I think of it like it's a solid-state technology solution. And I mean, ultimately, I think a lot of us, we aim to run. I mean, we always say, I wish I could run my 1 terabyte database in memory. Yeah, on surface, it feels very good, it looks very good, and reads are fast. And of course, it's very simple. Just plug it in your server and you're ready to go. But think about a server where you have to populate half a terabyte of DRAM. Try to price it out. The server itself, number one, will be very expensive. And then you will have to pay for the DRAM, which itself will be another expense. You will obviously get a lot of benefit in terms of reads. But if you have any kind of environment where you're doing a lot of writes, your benefit will be limited. Because any writes you do, they still have to go and hit the persistent storage. And then again, because it's a pure memory solution, every time you bring up your server, the initialization will take longer. And every time you reboot your server or you have to restart your server, that flush back to the persistent storage will again take a very long time. Then there are SAN attached SSDs. So based on what I said, if you look at that card, you know that it is in server storage. So it is a very anti-SAN model. Now, believe me, we don't say that, look, you can get rid of your SANs or you can get rid of storage arrays. At some point, the reasonable model is you come up with a hybrid where you have part of your stuff on your SAN or your storage arrays and part of it on some sort of solid-state technology solution inside your server. But they have these solid-state cards that you can actually plug in your SAN. So the cool thing is then they work with your SAN infrastructure. You don't need to change anything. And then generally the SAN provider gives you the software that manages the data movement. So obviously if you're plugging in something like this in your SAN, then it is going to be used as a cache. And what gets in the cache, what gets populated in the cache, and then how does it get flushed out will be managed by some vendor proprietary software. But again, the problem is, for that specific context, generally it is problematic to realize high densities of these SSD solutions that are plugged inside the SAN. They're very expensive. And then let's think about the promise of performance. If you have your servers here, and if you have your SAN here, the way they're being connected is via a network connection. And generally it is 1 gig E. If you are accelerating, if you are putting cache on your SAN, that means there is still a limitation, there is still a bottleneck of that 1 gig E connection between your server, where the data ultimately needs to get, and your SAN. So it's a little bit muddy. This technology is meant to give us performance, and yet it is designed in such a way that it kind of shoots itself in the foot. Then there are pseudo PCIe-based SSDs. Now, don't try to Google it. I don't think there is an official term called pseudo PCIe-based SSD. It's something that I coined this morning. At least I'm honest. So you will find some solutions out there where if you look at the card, if you look at the device, it has a PCIe connector. But if you look closer, if you know enough to look at visually at the product, you will start realizing that what they've done is they have essentially taken simple SATA-based modules, SATA-based SSDs, if you will, and they simply have packaged them on a single board. And normally when that is done, then they put a RAID controller on that board. You will see batteries on those things. Sometimes they put a little bit of DRAM on those boards. Sometimes they put their own CPUs on that board. Problem is, if you look at that, number one, just because it has a PCIe connector doesn't mean that it is actually going to give you the benefit of PCIe connected device, because it will still be bogged down by the SAS and SATA protocol translation requirements. And second, it has a RAID controller, which means, again, that sort of model has shot itself in the foot in terms of trying to deliver the performance metrics. So it's, again, I feel that it's a pretty poor architecture. It is designed to fail. And then there are native PCIe-based SSDs. I may be a little bit biased, but at the moment, as of now, I think that Fusionio is the only one who has this. And there is no secret. I think any company can come up with this. It's a question of how much effort are they willing to put into manufacturing and architecting something like this. So higher densities in smaller form factors. So you saw that card. That was a 320 gigabyte card. I mentioned that we also have a card which is not much bigger than this. And that is a 640 gigabyte card. And in a few months, we will have a card that will have 1.28 terabytes. Yeah, one card. Lengthwise the same, and height-wise maybe double. So just to give you an idea of how far server vendors have come to accommodate something like this, today you can get very easily a server from IBM or HP that can take 8 of those 640 gigabyte cards that I'm talking about, which means a card that is twice as high as this but the same length. And in a few months, we will have 1.28 terabytes. That means you can materialize more than, in a few months, you can materialize almost 9 terabytes of Fusionio storage in a server. So we talked about SAS and SATA, and we said that the interface bus itself has a limitation of, let's just say, 700 megabytes per second, because that's the latest protocol that's coming out. Today, if you have a PCIe Gen 2 slot in a server, which is very common, and if it's a by 8 slot, then that has a performance cap of 2 gigabytes per second versus the 700 megabytes per second. So that's point number one. You can deliver the throughput that is required for churning your data set. Number two, because it connects on the PCIe slot of a server, it is that much closer to your CPU. It doesn't have to worry about SAS and SATA translation. Therefore, compared to almost every other storage solution, this product, if you have a native PCIe-based product, it should be able to give you a latency on a microsecond scale. Whereas all the other technologies give you a latency on a millisecond scale. That's 3 orders of magnitude difference. But just like any other technology, there are some provisions here. So it does require drivers. And it's all dependent on what operating system you have. Now, obviously, I'm here, which means we completely support, Linux, Unix, and we are making, we support Windows. At least this product does, and we're making progress in other operating systems as well. And even though it's not fair to evaluate it based on dollars per gigabyte, but that is what everybody will do, because that is what everybody has been doing. So on that scale, yes, it does look to be expensive, only on pure dollars per gigabyte. With time, I'm quite confident that a new metric will become predominant, and it already is happening. When you're looking at something like this, the right metric to choose is performance per dollar. How many IOPS per dollar, or how many megabytes per second per dollar, depending on what is important to you. That is the right way to evaluate it. And as I mentioned, if you look at this card, you don't really know. It's very hard to tell the architecture. How is the data protected? Where is the RAID? Where is the controller? Where are the batteries? What kind of capacitors are you using? So it just takes some digging. If you are evaluating a solution, I urge you to ask them the hard question. Ask them, even if it takes time, to explain to you how is the product architected. And it's not hot swappable. So once you plug this in your server, if you need to replace it, you need to turn off the server. Is this a potential solution to the problem of disk I/O? The best way to understand this is, on one side you have DRAM, and what we really like about DRAM is that it is super fast. What we don't like is that it is volatile, it is very expensive, and limited capacity. Now, of course, you can realize a lot of capacity of DRAM, but then it starts to become exorbitant. Then you have disks, and what we like about disks are that they're non-volatile, they persist the data, they are cheap, and they give you pretty large capacities. But what we absolutely hate about them are that they're very, very slow. So if I was Tony Stark, and I had that cool interface where I could mix and match and do cool things, I would like to combine the best bits of DRAM and the spinning disk into one product. And this is exactly what these two gentlemen did for us. So David Flynn is our CEO, and Rick White is our CMO. And they gave us I/O memory. That's all I'm going to say about here. I've already said enough here. But this thing, it behaves like the dream product, like Tony Stark would want. It's reasonably priced. It is very high performance, pretty much not quite DRAM, but almost there. And at the same time, it has persistent storage. So once you turn off your server, data stays on it. Why do we call it I/O memory? I mean, I've been telling you all the time that, look, this is the hard drive. You store data on it, and data gets saved. So why call it I/O memory? Well, to understand that, on this graph, what you have is you have different kinds of storage options, and they are mapped based on how far they are from a CPU in a server, because that ultimately controls the disk access latency. So as you can see, the L1, L2, and L3 caches, they are on the CPU, and therefore they are the fastest. They give the lowest amount of latency on a nanosecond scale. On the other extreme, you have the traditional devices like SANs or RAID devices, and they are the furthest away from your CPU, and therefore they work on a millisecond scale latency in general. The SSDs, and here I really mean the SAS and SATA SSDs, or Pseudo PCIe SSDs. They are a little bit faster, sure, but they haven't broken the barrier. They still work on a millisecond scale latency. BioMemory, as a product, changes that. It breaks the performance barrier. It gives you microsecond scale latency because it sits that much closer to the CPU. And by the way, I mean, if there was a product tomorrow, if it was properly designed, anybody can do it. It would be right there as well. So it could be anything. What we find is that a lot of people, when they take this device for testing, they just love the simplicity of it. That it just becomes a disk, you put everything on it, and you're done. You're home. Everything is working just fine. So many people actually like to replace the direct storage with this. But in many cases, that's not practical because the database can be huge. I mean, even with the capacities and densities that you're capable of, what if your database is 10 terabytes in size, 20 terabytes in size? Possible. It's there. Even I wouldn't recommend that you materialize a server with 20 terabytes of Fusionio, unless you are some defense company or some government company that really needs to do their stuff. So what people are finding is that they're finding amazing use cases of using any SSD solution as cache. So good example is Flash Cache by Facebook. So Facebook recently released the code to everybody, and they call it Flash Cache. And what it is it allows anybody to use that code, take any solid-state storage option out there, and turn it into a cache for your data store. And I believe that they have two versions of Flash Cache. One is where if writes are happening, they just pass through. So there they instantly hit the persistent storage. And the second version is where they actually bash the writes in the solid-state storage option, and then they get persisted on your other persistent storage in a batch. So you can use this to support your Flash cache, or you can use anything else. In fact, Vadim has been kind enough to be doing quite a few benchmarks on it, and he's been using various SSD options there with Flash cache. And I think there is an excerpt on Flash cache with Fusionio as well there. So what I'm trying to say here is that if you look at BioMemory, even though it is persistent, I don't know if it's blasphemy to say this is persistent memory, but by nature, it actually acts like memory in terms of performance and in terms of reliability. In a few slides down the line, I'm going to talk about some of the concepts and features that we have put in, at least in this product, to make sure that you don't think of this like a disk, but you indeed think of this like your DRAM. So let's just jump into it. Certain architectural highlights. Reliability, obviously, is very important. So what we've done is there is magic in place, and we actually have more NAND flash on the device than the capacity that is advertised. I believe it's roughly 20% more. That, by the way, is actually a very good metric also to evaluate a potential vendor when you're going out there. Ask them, by how much do you over-provision your device? Now, if they say, oh, we have 100% over-provisioning, that sounds very good. You're getting 2 for the price of 1, right? Not really. If they are over-provisioning by 100%, that just talks about how confident they are in the reliability of their product. If somebody can tell you today that I am over-provisioning only by 5% or not at all, you should go with that vendor, because that means that vendor has figured out how to give you the reliability and is absolutely confident about it. So we over-provision by about 20%. And there is a RAID. There is the way they've implemented this. It's called N+1 redundancy, but it's a simple version of RAID. So what that means is that even if a chip dies, the card just continues to function. Your data is safe. It's protected. When individual pixels die, again, there is reserve space here, and the algorithms are constantly monitoring which pixels are dying. It takes them out of circulation, and it gets from reserve. Also, generally, if you take this card and if you format it by default settings, it serves your needs. But once in a while, you get into requirements where the writes or the intensity of write is much higher than normal. When that happens, then our software, we have using software, it is possible to reformat it and sacrifice a bit of capacity and increase the reserve space. And it's modifiable. You can do that. Now, once you do that, then you actually get even better write performance. You know, when I was talking about limitations of NAND flash, we talked about SLC flash and MLC flash. A lot of vendors, they are only giving you SLC flash-based products. They are not even touching MLC. Again, it just talks about their confidence in how much they have done, how much they have put in to give you a product that makes sense. We at Fusionio, we are doing very well with MLC. And a lot of customers are buying it. They're using it. Why? Because we have figured out a way to deliver almost SLC-like performance, and we have figured out how to give you almost the SLC-like reliability and life. And we have done it. And the fact is, as time goes on, I don't know if you know, but NAND flash is getting denser and denser because that is what economy dictates. Ultimately, it's in the best interest of all the companies to push more MLC than SLC, because at some point, SLC just becomes very, very expensive. It becomes very, very cost prohibitive. Imagine trying to materialize 10 terabytes of SLC-based storage. It's not practical. And it doesn't need to be, because MLC is doing its magic. You just need to know how to do it. So again, you know, when you're evaluating your solutions, find out, can you do the job with MLC products out there? Don't fall into this trap that, oh no, I only need SLC, because that's what I've read and that's what the fact. On our card, you know, we don't have any embedded CPUs and we don't have any embedded DRAM. And there are good reasons for that. It's very important to make it clear. Because we don't have these things on our card, so we use those resources on the host. So we used host CPU and we used host DRAM. Is that a bad thing? So let's talk about CPUs. When I started this, I already mentioned that because of the unbalanced systems, your CPUs are idle anyway. They're not really doing their job because they're waiting on the disks to do theirs. This technology opens that bottleneck. Now, we do utilize, you know, a bit of your CPUs, and how much we utilize depends on what kind of load you're putting on it. But, you know, ballpark figures, 5%, 10%, 15%, no more. But the good thing about that is that this technology grows with your server, which means 3 years down the line, when you upgrade your server to a better and faster CPU, this card gets that much better, grows with it. As opposed to when you put and embed a CPU right on it, that's it, you're stuck. You can't do any better than that. Now, let's talk about memory. So as I mentioned, many products, they put memory on the cards themselves, and they use it for caching. Problem is, then that introduces complexity in terms of how do you ensure the data doesn't get corrupted when it's being transmitted back and forth? How doesn't it get lost? because DRAM, as you know, is not persistent. We don't use DRAM for caching the data itself. We just maintain a map. It's a map of counters, the real data that reside on these NAND flash chips. And then there are 3 copies that are maintained at any point in time. One is in DRAM, and that's the one that is actively being used, and that's how we are able to do things really fast. We are able to resolve the maps really fast. And then there are 2 other copies that reside on the chips themselves, and that is just in case something happens, it can rebuild that map. Sorry, did you say anything? All right. I can drink some water. I don't know about you, but I believe in Murphy's Law. And I know that if I drink water and speak at the same time, I'm going to spill it on my laptop. Let me know when. Thanks. So, we don't have a rate control on the card. Now, we do have a controller, but the cool thing is that it is programmable. Why it's cool? Because what that means is that even when you buy this technology, down the line, 3 months, 6 months, a year, when we discover something cool, when we discover that, oh, you know what, we can double the performance of your product, all we have to do is just give you an update, and you're done. Pretty amazing. It's a very simple design choice, but it ensures the best interest of anybody using a technology like this. There are products out there, so they use batteries. I think that's absolutely a terrible idea. Batteries die all the time, and they leak all the time. So imagine what will happen to your device when any of those things occur. One way that a lot of these devices, they maintain their data, i.e. say if there is sudden power loss and they try to persist the data to a disk or some sort of persistent storage, is they use supercaps. We don't use supercaps, we just use regular caps. The problem with supercaps is that there are some special chemicals. Again, the supercaps can go bad, and those chemicals can have adverse effects on the product itself under extreme conditions. But the regular capacitors, they're just fine. They've been proven, they've been there for so long. And of course, I mentioned no onboard rate controller. The benefit of that is there is no performance cap, and there is no single point of failure. We'd like to talk a little bit about benchmarking. So there are many ways you can do this. There is DB2, DBT2, which allows you to simulate a TPCC kind of test. Then there is Sysbench, and again, I've learned a lot from Vadim's blogs and Percona, so I thank Percona for that. I think they're pretty amazing. But I want to give you some caution. Evaluate your solution, but know this about benchmarking. It's synthetic. You're simulating something which is not real. So try to give your real environment a shot. Try it, and then see how your real environment responds to different products that you may be willing to entertain. Because the synthetic benchmarks, they never really give you an accurate picture of what you need. So what ends up happening is that you make decisions based on loads that you will never experience. And and again, the benefit of trying to test in your real environment is that you will root out those technologies that don't scale well. So it's a very common problem. A lot of solid-state options out there, they lose their performance rapidly under 2 main conditions. One, when they're near capacity, and essentially it has to do with how much reserve space they have or don't have, and when the load type gets mixed, so read and writes, and they're happening together. A lot of the SSD options don't handle these scenarios very well. So once again, do the tests, but try to evaluate as much as you can your real environment. High availability. So even though I have urged you to think of this product not like a disk, but more like DRAM in terms of reliability. So do you RAID your DRAM? Do you do a RAID 1 on them? Do you do a RAID 10 on them? Probably not. The promise of this technology is performance. So let it deliver on that promise. As you saw from the Cloudmark case study and the Answers.com case study, they rely on multiple servers to give them their high availability. So Cloudmark, on their servers, they use 2 I/O drives, and they are used in a RAID 0 concept. And they don't care if something happens to the server. Well, I mean, they care, but they're not worried because they have multiple slaves. So they can always recover. Answers.com, every server has a single I/O drive. Single one. The point I'm trying to get is that when people use this technology and they use it, they realize it is that they want to use the technology to give them the performance to the max. Now, when you start doing RAID 1 or RAID 10, you will obviously have a performance impact on your write, because now it has to write twice. So even though you can do these things, you can take these in your server, and you can do a RAID 1 on them or RAID 10 on them. We don't recommend RAID 5 on our card. But if you do that, then you are going to sacrifice a bit of write performance. And then think about this. So, and again, this is different because different people have different high availability needs, and for some it is okay. But no matter how much effort you put into making the disks redundant inside the server can still go down. The RAM can get fried, the motherboard can get fried, and that's it. The fact that you have the redundancy on the disk level can help that. So focus on the big picture. If it is important to you, try to think about high availability, but accomplish that using multiple servers. So, we do a lot of cool stuff, or at least I think we do. But there is also a green side of BioMemory. Now, when I was thinking about this, I said, should I say we make everybody else go green? But then I realized that can mean that we make everybody jealous, right? That's not so. So the test was, we took a set of 15,000 RPM fiber channel hard drives. And we wanted to drive a performance spec of 100,000 IOPS. Now, obviously, you need a lot of spinning disks to deliver that kind of IOPS, because a single disk at the most can only give you 250. When we did that huge collection of disks costed us 133K kilowatt hour per year. Was that? Where? Yeah. Right. I didn't bother reading the 493. Right. Yeah. No worries. So then we took the more commodity-based SSDs, the Intel, the Zeus, and they're pretty energy efficient. They clock at 3K kilowatt hour per year. But that's where we are. Less than 100. to drive that performance back. Now, that is a 1,300 times more energy efficiency. Obviously, if you have one server or two servers, maybe it doesn't matter. What if you have 100 servers? What if you have 1,000 servers? And then you have those huge disk arrays to support them. Can you think of the cost savings that you will get by implementing something like this? Now, that's just the energy savings on consumption. There is another additional energy savings here. So when you have, so look at this red graph. So you have, what, hundreds of spinning disks there? They're producing heat. And to keep things cool, you have to run your air conditioner. If you have a single I/O drive there, you don't have any heat because you don't have any spinning platters. So not only do you save on consumption, but you actually save on energy used to keep things cool. And again, the cost savings, they amplify the bigger your environment is. So in the end, I ask for your forgiveness if, this thing was a marketing spiel or you felt that this was a marketing spiel. That wasn't my intention. My intention was to simply come forward as a DBA and tell you about something cool that I found. I wanted to clear some misconceptions, and I want to urge you to get excited about this. I mean, don't go out and blindly buy Fusionio, but go and evaluate other vendors. Ask them questions. Ask them about their architecture. Ask them about reliability. Get excited. Work with this. This is still pretty cool and fairly new. So people are coming up with new use cases or unique use cases. The flash cache example by Facebook is a perfect specimen of that. Well, if you are in the MySQL space, then I have to believe that you like to tinker, that you like to create, you like to develop. Well, develop something cool. Develop something cool with this. And I'm always available for you if you need to reach me. You can email me at sumit@fusionio.com. I believe that I'll have an opportunity to upload these slides or give them to you somewhere. Fantastic. So you'll have the slides. At this point, I would like to invite my colleagues, Mitch Crane and Jamila, and as a team, we will answer any questions you may have. A good question. So our smallest card, which is an 80 gigabyte card today, the list price is around $3,000. And the biggest card that we have today, and so these are list prices. Obviously, if you call us and if you, we have partnerships with IBM, HP, Dell. If you go through them, you might get better pricing depending on who you are and who your vendors are. But the biggest card that we have, which is 640 gigabyte card, the list price on that is close to $14,000.
Yeah, it's certainly an option to just throw the logs on there, the things that are obviously taking more of the I/O away from everything else, and you will see acceleration there. Sure, and then you could have the more sequential access go to the slow store, which is better at handling. Uh, sure, and it's actually interesting because under the covers, we're implementing an append-based file system, and so you actually get some nice effects from appending long streams of writes to our drive in terms of saving the amount of metadata that we have to track, which then in turn makes everything faster. But yeah, I mean that's definitely another, and you know, like Samit was saying, like you evaluate every scenario, and I'm also a big proponent of that.
Right over there. The question is, how long does it take for these drives to fail? I'm going to repeat it for the camera. Question.
Do you know the numbers for the real? I don't know off the top of my head. Or you're still mic.
Oh, good, sorry. So I'm required not to give you a number in terms of years for that question, and I'll tell you the reason why. So what's happened in the past is obviously, you know, we have different lines of products. We have MLC-based drives, and we have SLC-based drives, and the numbers are different for them. But every time we have quoted these, they end up on a blog without the distinction of MLC and SLC. So then we have our customers calling us, hey, I got this, and I just heard that you told me that this was the life of this product, but it's really this. That's because the blogger failed to mention or make a distinction between MLC and SLC. But this is what I can tell you. It's about how much faith we have in our product. Our products have 5-year warranty on them. So we believe that they will work for you for at least 5 years. Now, I can tell you also that estimate is conservative. As I mentioned earlier, the reason why we didn't put one of the reasons why we didn't embed a CPU on that device is because we know that you can hold on to these cards a lot longer than you can hold on to your servers. So a time will come when you will either have to replace your server or upgrade your server without actually having to replace these. And so that's why that point that these things actually grow with your server is very important. You know how long we have had production customers?
So the first real production driver was released, I think, in April of 2008, and that was I believe it was the 124 driver. The product was in development for about a year before that, from April 2007 to April 2008, and it was well, you saw the picture of the two founders. The device was incepted by them many years before that, and kind of things just kind of came to where you know, iPhones were so prevalent, and everyone's buying all this consumer flash. So the price point of flash got to be in a sweet spot, and you know, they were able to take this architecture that they've been dreaming of for so many years and realize it, starting in about 2007.
So if I may add a little bit of color to that, normally when people ask the question of how long this has been in circulation, the primary reason or motive behind that is to judge its reliability and endurance. No, absolutely. But it allows me to, it gives me an opportunity to tell you something that perhaps will help you make more informed decisions. So in this short period of time, Fusionio has managed to make official partnerships with big-time vendors like IBM, HP, and Dell. Now, I can tell you that they are not going to partner with any company without subjecting their products to a rigorous amount of testing. I mean, what happens when sudden power goes off? You know, reliability. Just I believe HP has something called a meat grinder, or
right. And the server vendors. I mean, their name is on the product that's being sold. The I/O accelerator is an HP product, so they're obviously not in their interest to release something that they don't think meets or exceeds all of their expectations for reliability and quality.
Sorry, can you repeat your question?
Reserve space.
You know, different vendors do different. I believe there are some vendors out there, they actually have 100% over provisioning. And yes. Yep. Right. Right. And then, and I think your question also was leaning towards, you know, what is that capacity threshold at which point the performance of the product takes a serious nosedive? So again, you know, I believe it's called Tom's Hardware. There is a website called Tom's Hardware, and if you Google and search them, they have done some benchmarking exactly on that in terms of, you know, how does the performance drop when the drive is nearing capacity, and again you will find that that Fusionio fared quite well compared to some of the others. Yes, sir. So I'll take that. Um, um, the one thing to keep in mind is that as a piece of hardware, this technology actually provides a lot more than what MySQL can actually use, or MySQL can actually use today. Now obviously, there is a lot of work that is being done. I mean, for instance, Percona themselves, you know, they have a plugin, and you know that optimizes on that, and therefore is able to deliver much higher performance on, say, Fusionio card, and there are some benchmarks on that. So the thing is, because this technology is so new, there is still a lot of work happening to actually be able to utilize the true performance of it. In terms of comparing it with, you know, other brands, OCZs, and I don't remember those numbers, but again, I think if you look up Vadim and Percona, you know, he has quite a few tests that he compares different technologies, and you know, I'm sure you will get your numbers there. You
So, uh, so we have customers using this product in a variety of use cases. So, for example, if you have high read or high write requirements, simply doing a RAID 0 stripe will get a near linear performance increase. So, for example, we have customers doing things like doing fast data capture off of Quadcon cooling microscopes, where they have really high resolution images. They need to be captured quite quickly before the image changes, and they're going to have to take another snapshot. So well, in this case, what they would do is they'd capture at several gigabytes per second.
The latencies are in microseconds or tens of microseconds, in order to keep up with gigabytes per second of throughput. Actually, yeah, it's interesting you should bring it up. So in terms of file systems first, we've found that XFS performs really well, especially with no barrier. And we're kind of working on quantifying that, and different people have different ways of, kind of checking up on that work. And we're releasing a Solaris driver sometime in the near future, which has ZFS support. And we've found that to be pretty interesting because you can actually kind of layer, like all the caching stuff is all kind of built in to the file system, so then you get a lot of advantages there. I would another note, ext4 could be very interesting because of the trim support. So our newer drivers will actually accept the trim command, which gives the kind of garbage collection process some good hints for how to clear up space for future writes. So yeah, I would definitely for now, my biggest recommendation would be XFS no barrier for MySQL. But we're constantly evaluating, and definitely if you guys are coming up with more numbers that we'd all be interested to see. And then the other part, sorry, what was the other part of your question again? IO schedulers. So we just hired the god of IO schedulers. Jens Expo is now on our team. So there's going to be some pretty interesting work coming there. For now, we definitely recommend the no-op scheduler. And you can also run the card in a mode, which is the default mode in all of the 1.2 driver releases, which actually bypasses all of the IO scheduler using the kernel's make request function. So as of the new driver, you kind of get the choice if you want to try using IO schedulers, you want to try CFU or no-op or deadline, or you want to just try shutting it all off and go straight to the drive. Because a lot of the time, and every workload could be different too. So yeah, it's another one that we love to bake off. I have to talk to Jens and get back to you on that. Right. So with the new driver, we're kind of partially releasing. We're keeping a core proprietary, and we're introducing kind of a layer with an API that is open. And so we're hoping that people will take advantage of that to do really cool stuff with our API, but we're still not allowing, deep into the guts, because it's when you look at this thing is so dead simple, and the contents of this FPGA are also, all it's doing is scheduling data to flow back and forth. So really the core of what we're doing and what gives us our advantage is in that core of the driver. So it's not going to be likely that we'll make much more of it open source in the foreseeable future. So, much to my chagrin, but hey, I need to make money too.
Right, there.
Sure. Yeah. We're constantly improving the garbage collection process, and there were definitely some issues there, and probably still are some issues we don't even know about yet. Where what ends up happening, you can imagine when you start to run out of space so imagine take all these chips and string them together into one long log. That's basically the simplest form of how we're using this device. So when you get to the point where there's no groups of free blocks, it's just the data is very fragmented. The garbage collection process is going to have to take some time to figure out how to clear up enough space to write down the next block. And keep in mind that because it's NAND flash, like Sumit was mentioning, before every write, you're going to have to erase. So it was kind of a there's some kind of worst case scenarios that definitely get called out in a few different places with some of our older drivers, where the groomer just looks like it's going out to lunch, and we've definitely put in a lot of effort. I wish I could claim more credit for it, but our core team of engineers is the one that's responsible for the groomer processes, and they've just been basically taking in all of the kind of pathologically bad scenarios and trying to come up with a generic solution to make everything work well. So, yeah, go ahead.
So based on the driver that is available for general consumption today, you need 2 gigabytes of DRAM to support 80 gigabytes of Fusionio storage for a block size of 1K. So it all depends on what is your environment and what is your average block size. So what that means is that, say, if you're so for MySQL, your block size would be what, 4K? Is that the most common? 512. All right. So if I'll just give you an example. If it is 4K, then your memory requirement goes down by a 4. But the base number is 2 gigabytes of DRAM to support 80 gigabytes of Fusionio storage for 1K block size. Now, in a few months we will have a new driver that's coming out, and it should be out probably within a month. And and under this driver, that requirement that I just quoted goes down by a factor of 8.
And then in terms of the changes that you need to make on the software side, when the driver loads, we will present as a block device. So it looks, the corollary of a disk would show up as dev SDA or dev SDP. So we show up as dev BioA, dev BioB. So it's however you would use SDS. You can partition it, do whatever you like to it, and yes, exactly. Partition. You can RAID them together with software RAID. Everything else is completely, hopefully, the same thing that you've been doing. A lot.
Right. So 9 terabytes. You're right. It again depends on what's your block size. 4K. I can't. But let's see. I'm gonna whip out my calculator.
Less than 100 gigs, but it's getting close.
For 640. Right.
That's pure overhead. So I mean, it's kind of goes back to what Samit was pointing out before. We want this to be as simple and straightforward as possible. We want it to do one thing and do it really well, and we're going to leverage the host to make that happen.
So actually, excuse me. So perhaps before you start entering into the 9 terabyte territory, then maybe a solution where the flash cache, where you don't need to materialize your full data set on Fusionio, and maybe you just need 1 terabyte of flash cache. by the way, Mitch is also a pretty accomplished engineer. So Mitch rewrote, I don't know if he submitted it, but he rewrote the memcache code. So memcached, as you know, it uses DRAM to do its job, to do its magic. And so many people have done this. And what they've done is they have taken the memcached code, modified it, so that as opposed to referencing DRAM, memcached code is referencing a solid-state device. So it can be Fusionio or anything else. The benefit of that being, say, I don't know if Google uses it or not, but think about Google and say if they had to use memcached servers, their cluster of memcached servers probably would be run into thousands. And the reason for that would be in each server, there would only be limited amount of DRAM. But you take that limited amount of DRAM and say you suddenly you have a server with, say, a terabyte of Fusionio, and now the memcached is actually referencing Fusionio, you can have a terabyte of DRAM or addressable memory per server. So a lot of our people are actually doing that, and they have been able to shrink the size of cluster. So Mitch has himself written a patch, and if anybody's interested in trying it out, get in touch with us, where it can reference the Fusionio drive as opposed to DRAM. So obviously, when we get involved with people, we have a qualification process, and if we already see a CPU problem, then we make them aware of, we remind them of how our technology works, and that they need to take care of the CPU problem. Because ultimately, if you look at what we do, we don't try to release the CPU bottleneck. In fact, we make the CPU work a bit harder, but we like to do it when the CPU is generally idling, which is what we find is usually the case. Depends on the load again, and what kind of activity is going on, but I would say 5 to 15%.
And I'd like to add to that is, the question is, why are you CPU bound? So in some cases, if you're CPU bound because you've got spin locks that are waiting on I/O, then we actually relieve that pressure by getting it faster. So in that case, people wind up. So it depends on why you're CPU bound. So we kind of try to understand that first. And if it works out, that it's not a problem.
Sorry. Oh, no, it's total. You're right. If there are multiple cores, multiple CPUs, the way this technology is built is that they all can access it directly, independently. Well, so I mean, so we're talking about latency here. So I believe we have some spec sheets there, and what do we do? 50 microsecond latency? That's what we on a single device. Yeah. Yeah. So we are proud of it. Sorry, I think I've seen you raise your hand quite a few times.
Yeah, that's correct. So it's and that's one of the enhancements that's coming with the driver that's going to be released along with Source. So up until now, we had to do quite a few one-offs where a customer would come and say, "Hey, we want to support, real-time Linux patch or something like," and we'd have to actually sit back and build it and hand it back to them. And so now it'll all be completely up to the customer. No problem.
By the way, I'm not a marketing guy,
Well,
but
sorry, I shouldn't. Yeah, that's a great
that's all right. No, so it's a matter of priority. Traditionally, what we find is that we don't want to define our promise of performance based on how fast you can boot your server, because we are not really in the PC space or the personal space, and that plays a more important role when generally we have seen that plays a more important role for a more consumer market than an enterprise market. And then again, boot times become a big problem, especially when there is a very high density DRAM kind of solution involved. But again, we don't, if somebody's using us, then they don't experience that problem of high boot times anyway. So it's just a matter of priority.
I can't think of places where we don't see it happen, honestly. Everyone can use this. It's it's kind of the inverse to the answer to the question, but yeah, it's in terms of the company, we're just always trying to make what we have. I think there's an AT&T commercial. We're trying to make fast faster, so that's what we just keep doing. That's what's on our roadmap. So the ECC is calculated. Yeah, it is calculated. Sorry, to think. I want to be sure I answer it. So the FPGA is very good at that kind of thing. Now, so in terms of those kind of load, and also the parity calculation, and so there's multiple banks of flash here. I kind of said before, you can think of it as one long log, and that's how we think of it in the software world. But in the hardware world, it's split up into parallel logs that all get the same operation happen on them in parallel. And so when we're calculating ECC, we're calculating ECC for everyone. And we've, in terms of the actual correction happens in the read path, right? So you write it down with ECC chunks. And then as you're reading it back, you can detect a certain number of bits that have had a problem. And it used to be the case that the corrections had to happen in the driver. And so we'd have to fire off an interrupt and go in and service it, and figure out what went wrong, do all these crazy polynomial calculations, and then set it right. And now we've actually been able to include a rudimentary amount of that in the FPGA as well. So Dead Simple has gotten a little bit complicated over the years, but we like to keep our HDL guys busy too. So. Oh. Yeah. I know that's on a slide. So I couldn't tell you off the top of my head. It's on a slide somewhere. Send us an email and we can dig out the numbers for you. Okay. Good. It's actually. Do you want to talk about the memory stuff, because we were just going over that?
Well, yeah, it really depends on the size of the data set that you're managing, because and this is what Sumit spoke to as well, you really get the advantage by being able to put more capacity inside each memcached server. Because if you can put in 320 gigabytes in each box, and then that's correspondingly caching that much more data. You've got terabytes behind it that you now can have a direct read cache available to it. That's where it's a big win for the memcached application. You know, depending on the size of the disk, if you've got a phenomenal amount of data, then you can go ahead with lower capacity DRAM chips, which are cost effective, and then just put that on top of the small data. So it depends really on how much data is behind your backend to see where the cost justification is for you.
And I wanted to add one interesting point that we've found recently. When you get to very large amounts of RAM, it actually gets very expensive in terms of latencies, which is something that we weren't completely expecting to see. But what ends up happening is, I mean, imagine you have this massive amount of RAM. If the locality of your application isn't pretty tight, then what ends up happening is every single fault you have is going to be an L1 fault, an L2 fault, an L3 fault, and you're going to spend all your time refilling cache lines. And so it actually, when you start to add up the latencies, we get pretty competitive even with a large amount of RAM. And a large amount is, more than 100 gigs or even, so I just thought that was kind of interesting.
When you increase the amount of RAM in the server, you're not increasing the L1, L2, L3 cache correspondingly. So the ratio increases significantly, and then you get a lot of cache miss. And that's really where you get a big impact in that regard. And also, the other thing is most server, if you go ahead and max it out, say 800 gigs, you're going to get probably an expensive. So typically, the number of go above that.
That's a coincidence. We have a lot of IBM servers customers. We have some Dell, quite a few Dell. It turns out that also what happens a lot of times is, and this is funny, you would think that when somebody's using us, they would be aching to do a case study, but a lot of times what customers find out is that they think that they have done something so amazing and unique that they want to keep it a secret. They want it to be their competitive advantage, and we see that more often in with some of our financial clients. And so unfortunately, there is a lot of cool stuff that we have done, but we can't talk about it. There is, I think I can say in general terms, we have also done a lot of cool stuff with government agencies. I can't even tell you which one. But again, it hurts us to that we can't talk about it at all. So there's a lot of stuff happens but we don't get to share it. Absolutely. Again, I think we have NDAs with some of those clients, but I can tell you that some of the very big ones. I mean, if you do a Google and if you think about the top 5 who are trying to rule the online gaming industry, they're most likely involved in
So we calculate a reserve percentage, and you can always check that with a status. There's a command line utility to check the status. And I believe the way that it's set up now is it burns down to 6% remaining reserve. Does that sound right?
Things about.
Maybe it's 6 to 10%. At which point it will actually it will definitely throw something in the log, and it'll put you in yeah, I think it's less than 10%. It'll put you in a mode which we call a right throttling mode. And so what we want is that people will feel that suddenly something has gotten much slower and go investigate. And if they're watching the logs, which hopefully everyone does, then they'll see the messages that says, hey, reserve is getting low. Hey, reserve is getting really low. Hey, we're going into right throttling mode. And before, we'll still allow writes in right throttling mode for a few more percent as it ticks down. And when it gets to some low 2 or 4% reserve remaining, we'll actually kick the drive over into a read-only mode. So that way, you don't give the user a chance to keep writing and keep wearing out the blocks such that you might lose data. It's a very slow, gradual death. So it's that we've got some charts of the reserve percentage over time, and it's a very slow. And with the caveat is, I think when it gets closer to the end, it speeds up a bit, but not by some dramatic cliff. Kind of, and it definitely gives you warning. So. I would imagine, and
So if I may answer that,
sure.
What you also get is we have an SNMP alerting built in, so you can incorporate. We have APIs. You can incorporate these things, and you can essentially build yourself a monitoring system. So then it's up to you as to what threshold you're comfortable with. Obviously, when you talk to our guys and when you're involved with the project, they will give you the more precise numbers as to what are those thresholds at which it goes into right throttling mode, at what point it goes into read-only mode. So then your job really is to set your alerts for yourself, so that you don't actually have to go and manually execute the command to look at the health of the device. You can simply you can automate all of that process.
What's an LM Sorry. Oh, right. Those bits are in the SDK, so you'll be able to build your own, roll your own, whatever you like. That's also partially exposed, and there's also you'll have the ability to tweak some of the settings on the groomer to say that one of the things that we do to enhance our wear leveling is we'll rewrite old blocks. So what's considered to be the oldest block on the device is going to get rewritten periodically, and that buys us a few things. It levels out the wear. It helps to consolidate fragmentation, and it also refreshes the electrical signals, because if you let it sit stale for too long, you'll actually start to lose data that way too. So a little bit, a few of those knobs will be exposed through the APIs once all that gets released. It's imminently going to be released. We're pushing it out the door as hard as we can. You call the wasp.
Excuse me. At this point, I'm noticing that probably it's getting late and people are leaving, and I don't want them to miss the opportunity to win the iPad. So if it's okay, I'll go around this side, and if please make sure that you hand your cards to either me, Mitch, or Jamila, and then we will have Erin, who has worked so hard to organize this, draw up a card. Obviously, what that means is that Erin. All right, we will have Mitch draw up a card. How about that? So, please. Thank you.